Okay, folks, I want to do a quick video introducing the chain rule for calculus. And in order to do the chain rule, well, we have to remember a topic from college algebra. So I say here, arguably the chain rule, which is particularly derivative rule, is going to be one of the most practical ones we use. And the reason why is because it allows us to take derivatives of composite functions. I.e., we use it for function composition. So you might be a little bit rusty on that, so I'd like to do a quick review. Let me just go ahead and put up a blank page here, and I'll just show you a quick visualization. So what often happens when we're dealing with a function is we think that the function has, let's say we're dealing with the function g here, and we've got the domain of the function g, and we're going to take a value and map it to the range of the function g. So that's typically what happens. We think of the function as taking values and mapping them from a domain set to a range set. So for example, we could take the domain value 0 in g and map it to the range value of 2, for instance. Okay? So that would be the ordered pair 0, 2, or put another way, g of 0 equals 2. Well, in function composition, what we then do is we then look at saying, well, this range set, or part of it at least, might be the domain set of some function f. So it could be the domain set of some function f that might get mapped to its own range set. And maybe I made my picture a little large here. So here's the range of f. And so we could ask the question, well, then maybe this 2 becomes an input value for the function f, and we could say, well, where does it get mapped to under the function f? And maybe it gets mapped to, I don't know, the sine of 2. So that's the idea of function composition. We take the initial input value 0, do g to it to get the first range value of 2, but that range value of 2 becomes the domain value of the second function, and we hop to this new range value, maybe in this case sine of 2. Okay. So one way to think about function composition is it says, okay, well, what would you get if you did this two-step process? So we could do the two-step process as one, okay? And in this case we would give the notation, we would say that f of g of 0, well, that got mapped to f of 2, which got mapped to the sine of 2. So this describes this two-step procedure in sort of a nice succinct way. So that's what we mean by function composition. So feel free to jot some of that down if you want. Pause the video, take some notes on that, but I'm going to jump back to our pre-work. So back to the previous page. So we're working with these composite functions, and so here I actually build a couple of functions through function composition. Here we've got the function g of x and the function f of x. And so this expression right here is read f composed with g of x. So practice reading that. It says f composed with g of x. Okay? So how do you actually do that? Well, and by the way, this notation you may not see all the time in this course, but it is the correct notation for function composition. But oftentimes we'll go ahead and jump straight to the definition of it, which says take f of x and input the function g of x into it. So here I've done this in two steps. Here I'm taking the function f of x, which is the square root of the input plus 1. So there's the square root of the input plus 1, but in place of the input I plug the function g of x. But then we can take this further because we know the rule for g of x. G of x is the x squared minus 3x function, and so we get the square root of g of x plus 1, and now we found f of g of x. I want to make the point that function composition in general is not going to be commutative. Generally, you can't just interchange it. Let's look at that. So keeping these two functions as before, the same g of x and the same f of x, let's find g composed with f of x. Well, that says we're going to take the function g, and in place of x, we're going to input the function f of x. So what is the function g? It says it's the function that squares the input and then subtracts 3 times that input. All right, well, let's do that. So we're going to square the input minus 3 times the input, but our input, rather than being a number, as it often is for functions, is itself a new function. So we inputted f of x into the x positions for g of x. Okay, just trust me, I got ahead and clean this up, and if you do so, that's what you get. The point of this example is to mention that f composed of g of x is not the same thing as g composed of f of x in general, so the order there does matter. So continuing on with this example, we've been looking at f of x, g of x being this function, f of x being this function, and I want to make a statement here. Notice that in the expression f of g of 2, that 2 is in the domain value for g, and g of 2 is a range value for f, but I'm going to say then, and I've actually got an error here, but not a domain value of f. Let's see why. So if we take f of g of 2, well, that requires us to compute g of 2. So g of 2 we would find is 2 squared minus 3 times 2, which is equal, that's 4 minus 6 is equal to negative 2. But what would I do with that? I would then, what would I do with that output, that range value? I would then try to input it into the function f, but notice f is not defined at negative 2. Okay? So in fact, f of g of 2 is undefined. And that's a particularly difficult issue with function composition. Okay, let's explore that just a little bit more here in question 5. Okay. So in question 5, we look at two new functions. We've got the function f of x is equal to 1 over x minus 1, and g is equal to the square root of x minus 4. So what's the domain of f? Well, the domain of f is all real numbers except for 1. So it would go from minus infinity to 1, unioned with 1 to infinity. And what's the domain of g? Well, the domain of g, since it's a square root function at minus 1, would go from 0 to infinity. Okay? So let's talk about the domain of their composition a little bit. Well, let's first ask the question, is negative 4 in the domain of the composition? Well, the answer is no, because it's not, because negative 4, if we write this in shorthand, it would be f of g of negative 4. So we would input negative 4, the domain value negative 4, or the value negative 4, into g of x, but it's not defined there. So why? Since negative 4 is not in the domain of g. Okay? So if you think of function composition, let's go back to that diagram here. If you think of function composition as a we're going to have a single function that mimics the two steps of first taking a value, plugging it into g, then taking that result and plugging it into f. Function composition mimics those two steps. In this case, we weren't able to even do the first step because 4 was somewhere out here and not in the domain of g. Notice that f of g of 4 is not defined. Why? Well, let's just look at that. F of g of 4 is equal to, that would be f of, we need to figure out what g of 4 is. Well, g of 4 would be the square root of 4 minus 1, which is the square root of, which is 2 minus 1. So that comes out to be 1. Okay, let's just double check that, make sure that makes sense. What was g of 4? G of 4 was the square root of 4 minus 1, which was 2 minus 1, which is 1. So that's where I'm getting this 1 from. But then if I try to input 1 into f, we see that this would be 1 over 1 minus 1. That is undefined. Okay? So notice that this composition, f composed with g, is undefined at both negative 4 and at 4, but for very different reasons. It was undefined at negative 4 because we couldn't even do the first step. We couldn't plug negative 4 into g of x. And then the problem here is that 4, even though it's in the domain of g, gets mapped to something that's not in the domain of f. Okay? So the answer to this question is that g of 4, which equals 1, is not in the domain of f. That's the problem there. Okay? So notice, of course, that we've already said that this function is not, f is not defined at y, so it's kind of a silly question. We've already answered that. Okay? But f of g of 1 is defined. Let's just check that. F of g of 1, well, that would be f of g of 1 but g of 1 would be f of the square root of 1 minus 1, which would be f of 0. And f of 0 is perfectly well defined. It would be 0 minus 1, and we get negative 1. So even though 1 isn't in the domain of f, 1, when we first plug it into g, gets mapped to 0, and 0 is in the domain of f. Okay, let's keep going. So here we're going to start over again. I've got two new functions, f and g, and let's actually compute f of g of 0, and we're going to do it two different ways. I've sort of already alluded to these two ways, but let's actually formalize this. So the first way is, let's do it as a point-by-point process. First, let's find g of 0. Well, g of 0 is equal to e to the 0 plus 1, which is equal to 1 plus 1, which is equal to 2. Okay. Then next find f of 2. So we took the domain value 0, we plugged it into g, and it outputted a 2. And then we're going to plug 2 into the function f, which is the sine, so that would be the sine of 2, and we'll just leave it there. So we see that f of g of 0 was equal to the sine of 2. And actually, if you remember, that's exactly the example that I gave you here. We plug 0 into g, and it spat out a 2. We plug 2 into f, and it spat out the sine of 2. Okay? So the way we just looked at that was a point-by-point way of doing this. Here's the second way, which is maybe a little bit harder, but also a little more sophisticated and useful going forward. So let's first find f of g of x. Notice I'm not plugging in, I'm not finding the point, I'm finding this new composition function. That is, by definition, f of e to the x plus 1. So everywhere I see an x in the expression for x, I'm going to plug in e to the x plus 1. And now I've built the composition function. So now let's find f of g of 0. That's just equal to sine of e to the 0 plus 1. And it should seem like we're doing the exact same thing. We are, but we're looking at it through sort of a different lens. Rather than doing the two-step procedure to find out that 0 got mapped to sine of 2, we built a new function, the composition function, that would do both steps at once. So that's a quick introduction or review, I guess, of function composition. And I've done part A here. I want you to try this. I'd like you to do part B here for your pre-work.